All right, now, so moving along with chapter 7, we've talked about how stresses are related to each other in different planes. If we can define stress in one plane, we can find it on a different plane or a different angle using the stress transformation equations. Now we're going to talk about how that stress is related to the actual deformation or the strain. Using Hooke's law, we're going to develop these equations, and then we're going to talk about how the strain is also, the strain in different planes is also related to each other using strain transformation equations similar to the stress transformation equations that were developed in earlier in chapter 7. So I'm going to keep these formulas handy because we're going to need them to solve some problems. But just review. So we're studying stress, but stress itself we can't really see. What we see is the results of stress. We see deformation, we see breakage, but mostly what we can observe and measure is strain. And so in our previous work we discussed and discovered that there were 4 stress relationships that were dependent only on geometry. That's the stress transformation equations already developed, as well as Mohr's circle. There was no material consideration in those things. Only the stress analysis, if you will. So they were valid for all materials, whether linearly elastic or not. All of those stresses on different planes could be computed. So now we're going to consider how that strain, how that stress causes a strain or deformation in a variety of ways. Okay, so when we talk about strain, these things are dependent on material properties. Remember from chapter 1 that Hooke's law defines the relationship within the linearly elastic region of sigma is equal to E modulus of elasticity times epsilon, which is this linear strain or the actual strain. Now we're going to look at the stress element as a 3-dimensional object a little bit. Here you can see that if we pull on this little bar, it has a beginning length of x. We're going to stretch it with some force, and it's going to have a strain of delta x over x. And because it's only in one dimension, we know that sigma is equal to p over a. Sigma is also equal to E epsilon, so we can suggest that P is related to strain by these 2 constants, which are the modulus of elasticity and the beginning area. All right. Now, but also recall that because of Poisson's ratio, we know that there is actually going to be a change, not just in x, but also in y and in the thickness. So we have, if our element or our object has a beginning dimension of x and y and t, as we stretch it, y is going to become y prime, t is going to become t prime, and x is going to become x prime, such that by Poisson's ratio we can say with linearly elastic material and stress and force in only one direction, we can know by observation that x prime is greater than x, y prime is going to be less than y, and t prime is going to be less than t. And we did that in chapter 1, I believe. Now, what we have now is an object not under stress in one direction, but stress in 2 directions. And so we're going to define plane stress as a situation where there could be stresses in both x and in y, and could be shear. And all of those things could be occurring at once on an object or an element, and there will be strain or change in all 3 of those situations. We're going to have strain in x, strain in y, and strain on our shear strain, which means a change in shape. But also, we're going to have a change in thickness as well. Now, what the deal is with plane stress is it says that we understand there's going to be a change in thickness. However, there is no stress in the z-axis, no stress causing that. So it's going to shrink, but we can't have any forces or stresses in the z direction. So again, what we discussed in the previous page is that one-dimensional stress will get strain in all 3 axes. In 2-dimensional stress, we can't just suggest that we're going to get predictable strain in all 3 axes, and it does become more complicated. So in our textbook, we developed the strain transformation equations, which below, or right here, which apply in this situation. So the strain is related to the stress and Poisson's ratio in both x, y, and z by these relationships. And if you know the stress, then you can compute the strain, as long as you know Poisson's ratio. If you know the strain, you can also compute the stress. And so these are solved simultaneously, so that if you know this, then if you're looking for the stress, you'd use these equations. If you're looking for the strain, and then you'd use these equations. Okay. So we'll use those in a second. Now let's talk about shear just a little bit. Shear, back again from chapter 1. When an object is under shear, it is deformed into a little parallelogram kind of thing like that, and we define that that the deformation right here is this angle. We called it gamma. So if you have a shear in the XY face and you start with a 90-degree angle, you're going to warp it into a shape that looks like this, where gamma XY is in radians, and this little angle here, alpha, is going to be related to our beginning angle of 90 degrees, or pi over 2. All right, so we defined also that this new shape, and the warp that it incurs is related to the shear stress by Hooke's law for plane stress. Again, that was developed earlier in chapter 2, I believe, 2 and 3, but we're going to use it for plane stress here in chapter 7, such that gamma xy in radians is equal to the shear stress in that plane divided by the shear modulus. And we can also relate the shear modulus to Young's modulus, or to the axial modulus of elasticity by the Poisson's ratio. All right, so just a couple of notes then. The only way to get gamma is to have some shear. You can't get there by just having normal stresses. And in this plane, tau theta is equal to gamma theta g for any other angle. So in other words, we may be looking at this shear stress on another angle, and you'll be able to calculate the change in shape on that angle again by using Hooke's law for plane stress. And one more thing is that, again, you don't get any gamma unless you have some shear, some tau. All right, last thing is back to Poisson's ratio then. We can compute volume change under stress in 3 dimensions, or stress in plane stress, by this little formula, and where we have E is the designator for volume change, and that's going to be delta V over V, and it is 1 minus 2 nu, that's the Poisson's ratio, over E times sigma x plus y. Now, just look at this little element with me just briefly, and you can see that, and it's pretty easy to predict, that if you're pulling this way and pushing this way and this way, that you're going to get some stretch in the x direction, and you're going to get some shrink in the y direction. It's pretty easy that y gets smaller and x gets bigger when you have a force arrangement like this. However, if you have something like this, where you have sigma going this way and sigma going out, in other words, all 4 sides are in tension, you can't always say that you're going to get positive x and positive y. You have to use the stress, or the equations developed before the stress-strain relationships for Hooke's law, in order to find out what those answers are. All right, so let's do a little problem first. Here's an example, or here's a problem out of chapter 7, and what we've got is a rectangular plate in biaxial stress. Just a comment about the problems in this section. Pretty much they're all biaxial stress, meaning stress in x and y, and so no shear is what I'm trying to say. And so that's the one I'm going to do for you here, and I'll make one homework problem for you. All right, so let's just look at this. We have a rectangular plate. It's in biaxial stress. Sigma x is 67, sigma y is negative 23, so that's in compression. Has a dimension of 400 by 550 by 20 millimeters. It's made of steel and has a new Poisson's ratio of 0.3. So first of all, we're going to determine the maximum in-plane shear strain. All right, so let me just repeat our factors here. We've got sigma x is equal to 67 e to the 6. Sigma y is equal to negative 23 e6. And the volume is equal to 400 by 550 times 20. And if I multiply all that out, it's 4.4 e to the 6 millimeters cubed. Let's also draw a picture of the actual object. It's not really this shape. It says that it's 400 by 500 by 20. So in the x direction it is 400, and in the y direction is 550, and it has 20 millimeters of thickness. So that's kind of what we've got. And we have a sigma x going this way and a sigma y going that way. And again, no shear stress in this situation. All right, first of all, let's draw a little Mohr circle and make sure we understand what's going on with this guy. You don't have to do this every time, but I find it kind of helpful. So let's just draw a Mohr circle of this situation. So I'm going to call this my. Now what we can recognize is that if there is no shear, we know that that these are the principal axes. So I'm going to say that sigma x and sigma y are given like that, and that's going to be equal to our principal stresses, and that is equal to 67, and this is equal to minus 23. So because of that, then I know that my axis is over here a little ways, and I can find out the middle, which is right there, and C is equal to 45 e to the 6th, and we know that tau max is going to be right there, so tau max is equal to 45 e6, and tau max going down there too. Alright, so that's just a little review of, this is positive tau and that is negative tau. We did this in quite a few times in our homework and in class, so I'm not going to review that. But anyway, so what we can see is that that is our principal stresses, and we can see clearly that that our maximum shear is going to be there, and that's what we're looking for. We're looking for the gamma max at shear max. All right, and we know that because these are the principal stresses, we know that this is going to occur at 45 degrees. So I can actually draw a 45-degree angle, and this is really what I'm looking for, is what's happening at this 45-degree angle, because that's where the maximum shear strain will be. All right, so let's compute a couple more things. Let's find out what our G is. G is given by the equation E is equal to 1 plus nu, and that's equal to 7.692 e to the 10th. Okay, so pretty big. Now, what can we discover then? If we know our maximum shear and we know our G, we can find out our maximum shear strain. So that's given by the equation gamma x1, y1, or whatever it is equal to shear at x1, y1 over G. And so I've calculated my shear is 45 E6, and I've got my G as 7.692 E10th, and I can get that, and that is 5.85 e to the minus 4 radians. So not very much. Doesn't have much of a strain, of a change in angle, but that's what it is. All right, so let's continue on. That's part A. Let's determine the change in thickness of the plate. Well, the thickness of the plate comes from the equations here of strain in the x direction, strain in the y direction, and strain in the z direction. So this is what I'm going to try to find, is the strain in the z direction. All right, how can I do that? Let's do the strain in the z direction. Strain z is given by minus nu over e sigma x minus or plus sigma y, and all of those are given. So I can say that that is equal to minus 0.3 over e is, oh, I didn't even write that down here. Let's put there, e is 200 e to the ninth. So e is equal to 200 e to the ninth. I guess I used it down here, but I didn't reference it, so let's do it down here. 200 e9 sigma x is 67, and plus sigma y, but sigma y is a negative, so that'd be minus 23, and those are both e to the sixth. So I can get that is equal to 66 e to the minus sixth. That is my strain in the z direction. Now strains are going to be extremely small. You know, these are inches per inch, millimeters per millimeter, and so if you're talking about steel or aluminum or anything structural, they're going to be extremely small numbers. All right, so let's find out what our thickness is. Our delta T is going to be the change in thickness is going to be the original thickness times E in the Z direction. So that's pretty simple. That is 20 millimeters times 66 e to the minus 6. That's equal to 1.32 e to the minus 3 millimeters. So that is the change in thickness, and that's, I believe that's what we're looking for, the change in the thickness of the plate. All right, so that's my second answer. All right, while we're at it, let's go ahead and compute also our strain in the x and the strain in the y. So let's put x is equal to, let's go back to our equation. Strain in the x is equal to 1 over e sigma x minus nu sigma y. So that would be 1 over e sigma x minus nu sigma y. So that's equal to 1 over 200 e to the ninth times sigma x is 67 minus 0.3. Sigma y is a minus 23. And those are both e to the sixth, and so I get that as equal to 369.5 e to the minus 6. And then strain in the y direction in the same manner, 1 over e sigma y minus nu sigma x, and that's equal to minus 215.5 e to the minus 6. All right, so given our scenario here, this is kind of an important kind of situation. Given our situation, we suggest that delta T, actually this was a negative. I didn't do that right. That's a negative, so that's a negative, and so that is a negative too. So delta T actually gets, or T, the thickness actually gets smaller, which is what we expect in general. You'd expect things to get smaller. Well, actually, not necessarily. If you'd had compression on all four sides, the thickness could have gotten bigger. But in this case, we have tension on that, compression on that, and so the thickness of the thickness gets a tiny bit smaller. All right. Now, let's look at the strain in the x direction. The strain in the x direction is a positive number, so that says that x gets bigger, and again, what you'd expect here is because we have compression here, you'd kind of expect that the y direction gets smaller, and indeed it does. The strain in the y direction is a negative number. All right, so let's proceed on and let's try to find out the change in volume of the plate. All right, we're going to do that in two ways. First off, we're going to do this with, get another piece of paper here. We're going to do this by finding the new dimension in x, y, and z. So first of all, let's find out what our new dimensions are in z. So we previously computed that e in the z direction is 5, what did we say? Well, we've already computed the delta t, so it's minus 66 e to the 6, minus 66 e6. So I'm going to say that t2 is equal to t1 times 1 plus ez, and that's equal to 20 millimeters times 1 minus 66 e to the minus 6. Okay? And our new thickness is 19.99867 millimeters. All right, how about in the x direction? Ex is equal to, or epsilon x is equal to 369.5. E minus 6, that is a minus up there too. So I'm going to say that x2 is equal to x1, 1 plus 369.5 e to the minus 6, and that is equal to, and again x1 is equal to 400 times this, and that's equal to 400.1478. 1478. Now I'm going to use lots of decimal points here because what I'm going to end up having is the difference between two very large numbers. So if you do it this way, then make sure you use lots of decimal points, otherwise you don't get an answer that makes any sense. All right, how about in the y direction? Epsilon in the y is minus 215.5 e to the minus 6. So I'm going to say that y2 is equal to y1, 1 minus 215.5 e to the minus 6, and y1 was equal to 550, I believe. And so I get that is equal to 549.8814. Now, if you multiply those three together, you get a new volume. So T2 plus x2 plus y2, so I'm going to say that volume 2 is equal to 400,384. And if you recall, volume 1 is equal to 400,000. And so the change in volume is equal to 384 cubic millimeters. All right, so that's the way you can do the change in volume. It's a little bit tedious, but it's an important understanding to know how you get there. Let's do it one other way, and this was using the formula developed in the book, and I'm going to say that this is E, which is a unit volume change, which is delta V over V, and that's equal to 1 minus 2 nu over E times sigma x plus sigma y. And again, there's no sigma z because there is no sigma z. We don't have any stress in the z direction. All right, so let's go ahead and multiply that out. As you got 1 minus 2 times 0.3 over 200 e to the 9th, and sigma x is sigma 67 minus 23 e to the 6th, and you get that as the unit volume change is equal to 88 e to the minus 6. Okay, so it's positive, and so that suggests that the volume actually does get a little bit larger. Well, in fact, we noticed that up there too. But now let's go ahead and multiply that by our volume. So I'm going to say our new volume, or our delta volume, is equal to E times the volume, which is equal to 88 E minus 6 times 4.400 e to the positive 6, and we get that is equal to 300, and I multiplied that to get 387 0.2 millimeters cubed. Actually, let me change this back here. I did this again, and I think I actually did get this closer. I think it was 386.805. 386.805, so it was actually 387. And that agrees with doing it with this other method. So both ways work, and this is a little bit easier, but it's very important that you understand that this is a compatible and appropriate way of doing it as well.